All right, so here we go. Let's get started here. So we can make it through enough of these notes here. All right, so today we're going to take a look at it. So we'll look at something known as calorimetry, and also we're going to look at this fancy term which is called enthalpy. Really fancy term, but it's pretty easy to understand once we take a look at it. After that, we'll talk about what's called the heat of reaction that goes along with these chemical chains. And let's just jump into these notes here. You remember, yesterday, we kind of looked at this problem here. We had that piece of silver that was at a certain temperature. And if you remember, basically what we did is we said, hey, we've got, in this case, a piece of silver at 96 degrees Celsius. We got our 25 grams of water that was in the beaker. And then we kind of took the silver, transferred it into the beaker. And what we're trying to do is see if we can figure out, in this case, what the mass of the silver was. And yesterday, successfully, we were able to kind of figure it out. And one of the things that we kind of figured out is in order to solve this sort of problem, we had to go to that Q positive equal to Q negative. Now, let's just think about this for 1 second. When I take my silver and I plop it over here into this water, so we said that we're going to have 25 grams of H2O here. So I'm going to take the silver, which man, it's pretty hot. I'm going to put it into the water. The heat, of course, is going to go into the water. Is heat going to go anyplace else?
Will it go into the air? Like it won't all stay into the water?
Okay, so some of the heat is going to go into the water. Some of the heat from the water is going to go into the air, right? And then some of the hot silver, when it goes down there,
Will it make like the glass?
absolutely, it's going to make the glass warmer as well. Well, that's a problem here. Because according to this equation, it says all the heat that is lost by the silver better end up, in this case, in the water. Which means that, hey, if some of the heat is going into the air, some of the heat is going into the glass, then that means this setup right here is going to lead me to having some sort of experimental source of air. Because some of my energy is being lost here. Now, one of the things that we have done in chemistry is we looked at ways in which we can actually improve this experiment in this case. Because if you think about it, in order for this thing to be kind of true here, is I need this to kind of be like its own little micro universe in this case. Which means I need to make sure that my container will not accept heat in this case. Because if my container won't accept the heat, then I know instead of some of the heat going into the glass, it's just going to kind of feed into the actual water. Now in chemistry, anytime we want to make a really accurate measurement with regards to how that energy is being transferred in the form of heat, then what we're looking at is calorimetry. So when I want accurate and precise measurements with the amount of heat for a chemical or physical process, calorimetry is what we're looking at. Now, for calorimetry, in order to get this accurate measurement with regards to the heat, one of the things we have to use is this thing called a calorimeter. And a calorimeter is really just going to be a device that is going to be an insulator. It's going to say, hey, you know what? If I have, in this case, going back to this example right here, if I have some really good insulator right here, then an insulator is like somebody who says, I don't accept heat in this case. Give you a good example. If I take some hot coffee and if I pour it in the glass, is glass a good insulator? No. That's why if you have a glass mug, it has a handle on it so you won't burn your hand. But at the same time, if I wanted it to go into a container and I could still hold that container without it burning me, I could use something such as a styrofoam cup. Does anybody use those things? And if you pour boiling hot water in there, you can barely feel any presence of heat coming off of it. And that's because that calorimeter, that styrofoam cup, which is acting like a calorimeter, is not accepting heat. So in this classroom, our little go-to device that we will use when we do our experiment is we're going to have this calorimeter that is going to be a styrofoam cup. It's a really nice, cheap insulator that's not going to accept any of the heat, which means that when I add something to the water, if that device is not accepting it, then the heat is feeding right into the water where I want it to actually go. So once again, an insulator is what we're looking at. And once again, styrofoam cups make excellent insulators. And if we have a really good calorimeter, then it now allows us to get this nice calculation of the Q positive and Q negative, and I don't have to worry about losing heat elsewhere in this case. Now, is the styrofoam cup the best insulator out there? No. There's better insulators out there. Let's just think about it. An insulator is something that is not going to, in this case, allow heat to escape out. But at the same time, it's not going to allow heat to get in as well, because that'd be bad as well if I had the heat start to feed in, because I want all the heat from the silver to go into the water.
Would you use like a vacuum?
No, well, I'm going to say no, but sometimes they use it a little bit. But that's not, I see somebody, anything. What is that thing?
Stainless steel?
That's not stainless steel. That's called what?
Oh, Stanley.
A Stanley. A Stanley is an excellent insulator. Hey, those, what are they called, Wallas or? Wallas. Excellent insulators. The Hydro Flask, excellent. If you think about it, one thing that I know about those things is you can put ice water in there. And you can put it in there early this morning before you leave to come to school. It could be at the end of the day, and can't you agree that you still have ice water inside of that thing? And that's because the heat from the atmosphere cannot get in there to warm it up, and it stays, in this case, cold. So ideally, are there better insulators than styrofoam cups? Absolutely. However, styrofoam cup is kind of like a little bit cheaper than having to go buy a whole bunch of these Hydro Flasks or Wallas or the Stanleys in this case. Yes.
Did you know that like Stanleys they became famous because there was a wreck? There was a car wreck, and it kind of.
Oh yes. I did.
It was known that there was a Stanley inside the car that was burning, and that there was still ice in the Stanley.
What's it?
Even though.
That's a good way of advertising, I guess. Your Stanley. Takes a tragedy, I guess, to figure out that hey, it's a really good insulator. All right, here we go, really quickly. This commercial is brought to you by University of Maryland College Park. At University of Maryland College Park, they have this thing known as the Women in Engineering Program. This is the URL. If you go to that actual website, you can find a little bit more about it. It's a fantastic program. If you're interested in engineering, what they'll do is bring you on campus for a week. They'll expose you to a whole bunch of different engineering fields that you probably don't even know about. A lot of us know about mechanical, electrical, computer engineering, but they introduce you to a whole bunch of different engineerings. When you go to the website, they're going to make mention that there is some fee to it. But the nice thing about this is I've seen places where they charge you an astronomical fee. They try to not charge you that much. Keep in mind, I can't tell you what it's going to be because every year it changes. Some years they get grant money. Like the government will hey, this is really great. They were trying to get more females into engineering. So sometimes they'll give grants to maybe College Park specifically for this program, and that will offset how much you want to actually, or you'll end up paying to actually participate. So I would encourage you, if I had other students who have been in engineering majors and have gone to this thing, and they told me that they really enjoyed it. So not a bad thing to kind of look at if you're interested in engineering at all. All right, continuing on here. We're going to take a look at now. And if you want to learn more about it, after looking at the website, you can talk to me and I can put you in contact with a student who's done it in the past. Just when you thought it was gone, it comes back. Thermostoichiometry. Yes, but the nice thing about thermostoichiometry is really easy. This is a lot easier than the gas law stoichiometry. And you're going to say when you start seeing it oh, I like this. This is not too bad. So let's see what's going on here. Thermostoichiometry, the portion of chemistry that deals with making chemical reactions using a thermochemical equation. Well, when it comes to chemical reactions, we're going to see that chemical reactions either be exothermic reactions, hey, they release heat, or they can be endothermic reactions as well, where, hey, they take in energy in this case. So what we do is look at what is a thermochemical equation. A thermochemical equation is nothing more than an equation that shows you, in this case, the amount of energy that's being released or absorbed. If you remember back in the first semester, we said, hey, this is a combustion reaction. Combustion reaction produces CO2 plus H2O, plus we used to put the delta symbol here. No more. Instead of putting the delta that is arbitrary and it doesn't tell you the magnitude of the heat, you're going to get an actual value that sits here. And if you look at it, the reason why, for me, thermostoichiometry is really easy is because if you think about normal stoichiometry, we always say, oh, it's mole to mole ratio that we have here. But if you look at it, watch what's going to happen here. If I have 1 mole of this methane going through the reaction, how much energy is going to be produced? 802.2 kilojoules. If I have 2 moles of the oxygen go through the reaction, how much energy do I get?
802.
If I get 1 mole of the carbon dioxide, how much energy? 2 moles of water. If you look at it, all you are going to do, literally, is set up a ratio between the moles and the energy. Instead of mole to figure out how much energy is going to be needed. And we'll do a couple of these problems, but it's not that bad in this case. Keep in mind, this thing right here is commonly referred to as the heat of reaction. I think it's an appropriate name because it's the amount of heat for that given reaction in this case. All right. And once again, we can use the heat of reaction to kind of set up some equivalent statements to allow us to be able to solve some problems. So if you look at this first example that I have right here, for this particular example, it says, hey, I got 10.3 grams of acetylene gas. It's burned completely. How much heat is going to end up being released in this case? So what I got here is I've got the following. I got 10.3 grams of the acetylene. I'm going to figure out how many moles, just like we always said. Whenever you're lost, if you are stuck, I don't know where to go. First place you go to is you go to the moles. So I got to the moles of acetylene, and then right here, instead of going from here to maybe figuring out how many moles of CO2 or the water, I'm just going to set up a ratio. For every 2 moles of acetylene, I get, in this case, negative 2,600 kilojoules of energy. Now keep in mind, if you want to, I have no problem with you doing this. Putting this as being positive right here. Putting this as, of course, be a positive number, but what you must do, and it is your choice which way you want to do, if you're going to have this as being positive, you must write released after it. Or, better yet, you can just do this, negative 515 kilojoules, because that negative, remember, that means exothermic. It means energy is flowing out of this thing. You cannot just give me, in this case, a positive 515, because anytime somebody says, hey, my answer is positive 515 kilojoules, I'm going to say, well, okay, you're telling me that this energy is endothermic, and it's not the amount of energy coming out, but I would have to put that amount actually into it in this case. Yes?
So would you always put that number as would you always put the heat of reaction as negative in the...
So long as the reaction is exothermic. Stay with me. I'm going to see in a second how you can figure this out really quickly, because it's going to be pretty easy in a second. If you look at this problem here, and better yet, before I even go to this problem, let's do this. No, hold on, because I need to wait until I show you something else first. Say I gave you a problem like this, where it's just simply said, well, how many liters of O2 at STP would be required to produce 23 kilojoules of heat? So I got 23 kilojoules of heat that's being produced here. And the question is just asking, what would be the liters of O2 at STP? Well, what I can do is I can take the heat that's given, and I know that if I had 2,600 kilojoules, that would equate me back to 5 moles. So what you're doing right here is you're really just going from kilojoules and figuring out how many moles of the oxygen you have by using the mere 23 kilojoules. It's going to kick out how many moles of oxygen, in this case, would have been used to produce that small quantity. And because they're asking for the volume at STP, I use the 1 mole is equal to 22.4 liters, and it kicks out exactly how many liters. At the same time, if you don't wish to do this, can't we agree that you could do this as well? You can plug in here, 0 degrees Celsius, which is 273 kelvins. You can plug in 22.4 liters. You can plug in this case, 1 ATM. You can solve for N. And then once again, it would also or solve for V. It would tell you the volume as well. I'm not going to do that, especially if it's at STP. I'm just going to bring in the 1 mole is equal to 22.4 liters. The next one, it simply says how many grams in this case of water would be produced if we had 560 kilojoules of heat. So if I have that amount of heat, then once again, I can easily set this thing up. I'm going to take the heat. I'm going to say, hey, for 2,600 kilojoules, that would be 2 moles. So clearly, I don't have 2 moles of water. But because they want me to figure out how many grams, I just go through and I say, hey, based upon this, I got 7.01 grams of the actual water being produced here. Heat of reaction. Once again, the heat of reaction, we're going to talk more about this. I'm going to show you a couple of things here that you're going to see that's going to kind of help you out a little bit as well. When it comes to the heat of reactions, the physical states of the reaction products are going to be given. Because one of the things that's going to happen is if you play around with the states of the reactants and products, the value of the heat of reaction can actually change in this case. Generally, when we look at the heat of reactions, they are generally studied at what's called standard condition. Now, this is different, because what we're used to is standard temperature and pressure. And standard temperature and pressure, which we call it STP, which we set at 0 degrees Celsius and 1 ATM. Well, one of the things that they started looking at is like, hey, if I'm going to start talking about how much energy is coming off of this reaction, do I really want to work in an environment that's 0 degrees Celsius? I don't think so. So what they did is they said, we got this thing known as standard conditions. And standard conditions, well, 1 ATM is like regular atmospheric pressure. We're about 1 ATM right now. 25 degrees Celsius, that is considered to be room temperature. So really when we talk about standard conditions, they're just simply saying that when they started to find out these values for the heat of reaction, that they're doing it under room temperature conditions and also the pressure. Here we go. New term. Change in enthalpy, which is delta H. Change in enthalpy is nothing more than studying, in this case, the heat. So I'm going to study heat. So it's just like Q. The only difference between Q and the change in enthalpy is the change in enthalpy has a stipulation that says that you must be at constant pressure. That's the only difference. Q is like, I don't care. You can change the pressure all around you want, but delta H, the change in enthalpy, says no, it must be at constant pressure. Now, what's nice about this classroom is that if we were to calculate Q, I believe the delta H is going to be equal to the Q. And the reason why is that when I look over there at my barometer over there, does the pressure really change in this classroom? I mean, it will, but it's going to take a long time for it to take place. So one of the things that you're going to see a lot is a lot of times they're going to use Q and delta H interchangeably. But keep in mind, delta H does technically say that, hey, we must keep, in this case, the actual pressure constant. So once again, with delta H, we're going to see that a lot of times the heat of reaction is going to be shown by having this delta H that sits there. I'm going to show you in the next slide that sometimes your delta H is going to be negative. If you get a negative value delta H, just like we said, if Q is negative, it's exothermic. If Q is positive, it's endothermic. Nothing's changing here. Treat it just like Q in this case. Which means that if we look at our thermochemical equation, such as this one right here, I got two ways in which I can express this equation. One way is to show, in this case, the heat of reaction. And keep in mind that anytime you see the heat of reaction on the product side, that implies that the reaction is exothermic. And the reason why I know this is showing exothermic is because energy is not going into it. Energy is coming out in this case. So when I see it on the product side over here, that automatically just tells me exothermic. Don't need to do anything. I see it on the product side, I'm just sitting there, I know it's exothermic. The problem becomes is when we decide to pull the heat of reaction out and have it set as my delta H here, my change in enthalpy. If you look at it, I cannot just simply say delta H is equal to positive 393.5 kilojoules. I can't do it. Because that, I said it was positive, that would mean that the process is endothermic. I need to put the heat on this side over here. What you would have to do is simply write down our change in enthalpy is equal to, and because it's exothermic, you gotta put a negative here. And your homework assignment tonight, I might give you a problem just like this, and then ask you to show the heat of reaction actually incorporated in the reaction. And you'll say, oh, if it's exothermic, I'll put it on this side. If the delta H, which I'll show you in a second, is positive, then I'm gonna take it and dump it on this side, because then it has to take the energy in order for the reaction to actually play out here. So to give you another example here, say I have this reaction right here. And if I ask you, hey, you know what, rewrite this, showing the heat of reaction actually inside the reaction, then what you are going to do is you're going to say, hey, it's positive. Positive means, in this case, that it happens to be endothermic. Which means that 129 needs to sit somewhere on the reactant side. I don't care if you put it here or you put it afterwards. It just needs to sit on the reactant. So I'm going to say 2NaHCO3 solid plus I got 129 kilojoules going to produce, in this case, Na2CO3 plus I got, what do we got going on here? 2 plus H2O as a gas, producing CO2 as a gas as well. And once again, you could have flip-flopped these, I don't, just so long as it's on the reactant side, that's all I care about. For the next problem, this one, I give you it incorporated in the thermochemical equation. I want you to pull it out and show it as a change in enthalpy, having it sitting separate in this case from the actual thermochemical equation. Yes. Absolutely. So I'm gonna write this thing. So calcium oxide reacts with liquid water to produce calcium hydroxide as a solid. And then my delta H, my change in enthalpy. Positive or negative? Negative. So negative 65.2 kilojoules. And once again, it is imperative that if you have that change in enthalpy, you must tell the person what in the world is going on here. If it's in the reaction, it already states it. Oh, you're endothermic. You're on the product side. You got to be exothermic right here. All right, what we're going to do now is we are going to go to our worksheet package and take a look at what you're going to be working on. So in the worksheet packet, you are going to go to the page right here. And you're going to see it says thermochemical equation and enthalpy worksheet. And you'll notice that it's going to ask you a couple questions like, under what conditions will the enthalpy of a process equal the amount of heat transferred in and out of a system? So when is it the two can be equal to each other? You'll have some other problems here. So for instance, maybe we'll do this one together, number 2. The question is, first of all, based upon the reaction, is the reaction endothermic or is it exothermic that you're looking at here?
Exothermic.
It's exothermic, so you'll just circle it. So circle exothermic. There we go. All right, and the next question, it simply says, how much heat energy is released when 540 grams of oxygen is being produced? Okay, see if you can solve this one. So you got 540 grams of oxygen. And they want to know how much energy is being released in this case. Once again, I'll help you out at least. There you go. What's going
Yeah,
on?
working on it. That's cool. I gotta go.
It's smooth. Hey, you saw that, huh? Okay. All right. Is everybody finished here? Give a couple more seconds. Let me see if I can find the answer myself. All right. Anybody want to offer up their answer? Which brave individual in here is going to raise their hand? I see one. Are you putting your hand up or are you just saying hi? All right, let's say that you're raising it. What'd you get?
I got 570
Kilojoules? 570. Let me just double check. Wait.
Yeah,
Try one more time. You got a slightly different answer.
Negative 570?
Anybody else get a slightly different answer? Let me make sure I did it right. Maybe I did it wrong. Oh, actually, I did do it wrong.
It's
Yeah,
probably-
you're right. You're right. It's negative. Thank you. -5. Okay. So if we look at it,
But do you 572 in graph?
so keep in mind, you got it. So if we look at it, you're gonna go in here. You're gonna just simply do the following: 32.0 grams of O2, right, per every 1 mole of O2. But then what we gotta do is we gotta go through here. We gotta use our mole to energy ratio, right? And it shows us right here for every 2 moles of O2 that's gonna contribute in this case 67.8 kilojoules. And once again, this is where it's your choice. You can go ahead and put the negative in here, which will kick out a negative, say, hey, that thing is exothermic, or you can get the actual answer and just write released after. One or the other. You can give me the negative or write release. So 540 divided by 32, enter, divided by 2, enter, times 67.8. And once again, with 2 sig figs, it looks like we're gonna get negative. I'm gonna go with the negative here. Negative 570 kilojoules, or once again, you could say 570 kilojoules released. Either one, it is your choice which way you would like to go. Is everybody okay with me?